In this video, I will demonstrate how to compute Fourier sine and cosine transform of a particular function. That is this example. Fx equals x minus x times exponent of minus x. We are required to compute the Fourier sine and cosine transform of this function. So I will provide 4 methods to solve this problem. The first, we consider this f, consider the primitive of this f, that is this capital F. Then by integrating by part, it is easy to see that the indefinite integral equals to minus exponent of minus x times x plus 1. But we observe that exponential of minus x times x is precisely our fx. So this is a nice property. Using this property, we see that since our small f, our function is the derivative of capital F, so we applied the property of Fourier sine and Fourier cosine transform. We see that what we want to compute, that is the Fourier sine transform of f. That is precisely the Fourier sine transform of f prime using the property of prime. The property of prime is here. The Fourier sine applied to f prime equal minus alpha times the Fourier cosine transform of the function. Okay, using this property, let's go back to our problem. Using this property, we see that f sine applying to f prime equals to minus alpha, f cosine applying to capital F. But as we know, capital F is precisely minus f plus exponential. So here this equals to the minus sign cancel. Therefore, we have alpha. Then Fourier cosine f, that is Fourier cosine applying to small f. Now, because capital F equals to minus small f plus exponential. Okay, so we have a Fourier cosine applied to f plus Fourier cosine applied to exponential. Okay, but on the other hand, the Fourier, let me see. Yes, we multiply alpha to the both terms. Then we observe that we know what this is. The Fourier cosine of exponential. We know this, the result of this. Okay, and similarly, we apply the Fourier cosine to small f. But small f is capital F prime, so we have this equality. Then we apply the property of Fourier cosine. Okay, let's check. Fourier cosine applying to a derivative equal alpha times Fourier sine applying to the function minus half of pi f0. Using this property, we can compute Fourier cosine applying to capital F prime equals alpha Fourier sine applying to this capital F minus half of pi f0. But f0 is minus 1, and f sine f, as we said, f is minus small f plus exponential. So this is just the Fourier sine applying to capital F. It's just the Fourier sine applying to small f plus Fourier sine applied to exponential. Okay, and then that is the result. Now we obtain these equations. These equations we have 2 unknowns. Okay, we have 2 unknowns. Fourier sine applying to f and the Fourier cosine applying to f is the unknown. So this is also unknown here. But this unknown, this we know the result of this. Fourier sine and the Fourier cosine applying to exponential, we know the result. So we can solve these 2 equations, which the 2 unknowns, Fourier cosine applying to small f and Fourier sine applying to small f, and then get the result. I will not complete the computation here. Okay, this is the first method we can solve this problem. Now let's go to the second method. The second method is from an exercise in our textbook. Okay, so for simplicity, we use capital S alpha and capital C alpha to denote the Fourier sine and the Fourier cosine transform of our f. Of course, the capital S here stands for sine, and the capital C here stands for cosine. So this is reasonable to just the notation. Okay. Now, by the definition, C alpha plus I sine alpha is what? C alpha is here. C alpha is the Fourier cosine transform of f. Therefore, this is C alpha. And similarly, sine S alpha is times sine alpha. Of course, we have an I here. That is this I. Okay. So we can compute the Fourier cosine and the Fourier sine at the same time using this equality. But having obtained this equality, the cosine alpha x plus I sine alpha x can be expressed in terms of exponential. That is exponential. Our fx is x e to the minus x, and the cosine alpha x plus I sine alpha x is exponential of I alpha x. Okay, then we can write this in this way. We can combine the two exponential to get this exponential. Then this is integral x times exponential. Of course, we can apply the integrating by part. So to apply the integrating by part, we need to move the exponential into the differential to get d e to the minus 1 plus I alpha x. Of course, you need to divide it to get this equality. You need to divide it minus 1 plus I alpha here. Okay, so then we can integrating by part. The coefficient we copy, and then the first term is the multiplication of the x and the exponential. The terms inside and outside of the differential d, that is x exponential. Okay. The second term is what? The second term is you switch the terms x and the exponential to get this integral. Okay. This is just a simple integrating by part. Now let's have a look on this term. This term, when x equal to 0, of course it is 0. How about the value of this term at the upper limit of the integral, that is infinity? Well, I will tell you that this is 0. X e to the e to the minus 1 plus I alpha x. No, sorry. When x equal to infinity, this is 0. Why this is 0? You might wonder because x is unbounded, but the exponential is very small. Let's write this in a more familiar way. E to the minus x cosine alpha x plus I sine alpha x. Okay, then you see that cosine alpha x plus I sine alpha x is bounded. The absolute value is not greater than 2. But x goes to positive infinity. But when x goes to positive infinity, the exponential goes to 0. Therefore, the combined goes to 0, because the exponential term decay to 0 very fast. Therefore, the effect that x goes to positive infinity can be cancelled. Okay, so this in conclusion, this term is 0. Okay, so this term is 0. Therefore, we can keep computing. This term is 0. So we write this term, copy it here, because the minus sign here comes from the minus sign in front of the integral. Okay, now this is the integral of exponential function. Of course, it is easy to find out that the primitive of this function is exponential over the coefficients. Then evaluating this at 0 and infinity. Similar to what we did here, we see that at infinity this term is 0. Therefore, the final result is when x equal to 0, the exponential is 1. So the final result is 2. The minus, because 0, for the x equal to 0, you need a minus sign. Cancelling with the previous minus sign, you have 2. And then you have pi times the square of the coefficients. Okay, now you simplify this complex value. You expand the expand the square downstairs to get this. Then you multiplying both sides by the conjugate complex of this number. That is 1 minus alpha square plus 2 alpha I downstairs and upstairs. Then the term on the downstairs is the sum of their square, the difference of their square, but the I square is minus 1. Therefore, actually, it is the sum of these two square, 1 minus alpha square and the 2 alpha square, that is 4 alpha square. Okay, then you split this into complex part and imaginary part. So you compare your left hand side, compare the complex part and the imaginary, compare the real part and the imaginary part of your left hand side and the final result on the right hand side. You see that the Fourier cosine equals this. Okay, and the Fourier sine, oh no, oh, this is bad. Fourier sine, yes, Fourier sine equals this. That is the result. So this is a very beautiful method to solve this problem. That is our second method. Okay, using the complex exponential. That is an example in our textbook. Now let's present the third method. The third method is just using the definition. So the Fourier cosine transform of our x exponential of minus x, that is our fx, by definition is this integral. Now, to compute this integral, we apply the integrating by part. Okay, we move the exponential inside the differential. Inside d, we move the exponential here inside d to get de minus x. Therefore, we need a minus sign here. Okay, don't forget the minus sign. Then, having writing the integral in this form, we apply the integrating by part. So the first term is the multiplication of the terms outside and inside the differential d. Therefore, that is x e to the minus x cosine alpha x, evaluating at 0 and infinity. Then we need to subtract the integral of switch the terms, switch the two part inside and outside d, switch. We get exponential, then dx cosine alpha x. Okay, this is just integrating by part. Now the first integral, we know, in our previous example, we just explained that this is 0. Okay, when x is 0, because there is a factor x here, it is 0. And when x at infinity, x exponential minus x goes to 0 very fast. Therefore, altogether, this go to 0. So, this term is 0. So now we compute the differential here. The differential of x cosine alpha x is just cosine alpha x plus x times differential of cosine alpha x. The differential of cosine alpha x is alpha sine alpha x. So we get this result. Now we can split this integral in two parts. This part and also this part. Okay, we split this integral in two terms. The first is exponential minus x cosine alpha. The second is what? The second is exponential alpha sine. What's this? This is just S alpha, right? This is just the Fourier sine transform of our function x e to the minus x. This is just our fx. Okay. And now the first integral is the Fourier cosine transform of exponential of minus x. The first integral is just the Fourier cosine transform of e to the minus x. This is a no result. Okay, you know this result. Or you can compute this integral directly, even if you don't know the Fourier, even if you don't know this is just the Fourier cosine transform of exponential of minus x, you can compute this integral using integrating by part. This is easy. Anyway, the result is pi over 2 over pi times 1 over 1 plus alpha square. And then the S alpha term we copy here. So we see that say alpha equals to a null function subtract a multiple of S alpha. Okay. Similarly, we start with S alpha. That is the Fourier sine transform of our function. And computing as before, we move the exponential into the d so that we can integrating by part. Okay, integrating by part, we get this result. Now let's have a look on the first term. The first term is obviously 0, similar to the previous one. This is also 0. Okay, this is 0. Therefore, our result becomes here. Here we compute the differential of x sine alpha x, resulting in sine alpha x plus alpha x cosine alpha x. Okay, so now as before we split the first is this integral. As you can see, this integral is the Fourier sine transform of e to the minus x. We also know the result. Or if you don't know, you can compute this integral using integrating by part. So it is not difficult to compute. Well, the second integral, what's the second integral? The second integral is precisely exponential of x times cosine alpha x. So this is just the Fourier cosine transform of our function. Okay, that is say alpha. Okay, so we have 2 alpha over pi times say alpha. Okay, so we have this two equality. What equality? We have say alpha equal 2 over pi 1 plus alpha square minus 2 alpha pi S alpha, and the S alpha equals to, sorry, this integral is also known. Yes, this integral is precisely this one. Okay, so this is alpha 1 plus alpha square minus 2 alpha pi. Say alpha. Sorry, I have a misspelling. This is say alpha. Okay, so solving this system, we have two equations and two unknown. The two unknown is say alpha and the S alpha. So you can solve S alpha and say alpha and obtain the result. Of course, I will not solve this easy problem here. Okay, this is the third method to compute our result. The last method is also interesting. In the exercise of section 6.2 in our textbook, there is a property. This exercise asks you to prove this equality, the property of Fourier sine. This property says that the Fourier sine transform of x times fx equals to minus the derivative of the Fourier cosine transform of f. Okay. Similarly, there is another property. The Fourier cosine transform of x fx equals the derivative of the Fourier sine transform of f. So what we want to compute is fx is the case where fx equal to minus exponential of x. So we applied this property to this function fx. So what can we get? So the Fourier sine transform of our function, that is x e to the minus x, okay, by this property equals to the derivative of the Fourier cosine transform of f. But our f is exponential of minus x, and we know its Fourier cosine transform. Its Fourier cosine transform is 2 over pi times 1 over 1 plus alpha square. So you're taking the derivative. This is a function of alpha. Taking the derivative of this, you get this result. Okay, so we immediately obtain what we want, the Fourier sine transform of our function. Similarly, to compute the Fourier cosine transform, we apply the second property here. This will be the Fourier sine the derivative of the Fourier sine transform of our f. F is the exponential function. So the Fourier sine transform of f is also known. This is an example in our lecture. Then you taking derivative of this function, you get the result. So this is the last method I will introduce. Okay.